Hey everyone, welcome to another video of going through chemistry passages. So first I'll show you guys a brief overview of the passage so that you can read through it, and then you can look at the questions as well, pause the video, attempt them on your own, and then we'll go through it together. And that's the passage. And then here are the questions: 41, 42, 43, and also 44. Alright, cool. Now let's start going through the passage together. So in this passage, class was studying electrochemistry. The instructor gave each student an unknown. Some of the data are shown in table 1. So let's just look at the columns: their student, their number, the nature of the unknown that they got, and then their measurement, either pH or E0. So we don't have to go through the details right now. We know what's in the table. We'll come back to it if needed in the questions. Some students require the Nernst equation, and equation 1 is shown over here. This is pretty simple. It's just an equation. If we need it, we'll use it in the calculations, but if you study electrochemistry, you should have already learned this. In equation 1, okay, so they're going to give us an explanation. N, which is over here in the denominator, N equals the number of moles of electrons transferred in the redox reaction, and Q is the reaction quotient. The expression for Q in terms of concentrations of reactants and products is written in the same manner as is the expression for the equilibrium constant, K, for a reaction. The standard cell potential, or E0, of the cell in volts of a galvanic cell is obtained when all the components of the cell are in their standard or thermodynamic states. Thus, E0 of the cell equals 0 when Q equals K. All the students studied the reaction given by equation 2. This reaction is unbalanced as it currently is, for which E0 of the cell was 0.23 volts. So here's the equation. This manganese reactant is reacting with this chlorine reactant, and then it's turning into these products. So that's a reaction. If we need it, we'll get back to it. If we need to balance it or anything, we'll do that if a question asks us to. Finally, it tells us the standard reduction potentials for certain electrodes are given in table 2. So how do we read this table? Standard reduction potential. So reduction potential means the potential of this element to be reduced, or not even an element, for a specific form of an element, because you could have different charges of the same element. But either way, the standard production for whatever's in the half reaction, standard potential for that to be reduced. So if it's higher up on the table, then that means that there's a higher reduction potential. It has a higher need to be reduced. Okay, so if I were to have two things that I directly compare, like say these two things, that's this copper and this zinc. Well, copper is higher. It has a higher standard reduction potential, so it wants to be reduced more badly than the zinc does. So if I were to have these two connected and I have those as my identities in the half cells, then copper would be the one that would be reduced. And very quickly as well, I'll just throw down this acronym, oil rig. What does this mean? Oxidation is loss, reduction is gain. So when I'm saying something wants to be reduced, that means that it wants to gain electrons. And all of these half reactions that you're seeing in the left side of this table, those are reduction reactions because electrons are gained. So that means that if we were to put two of these things together, we'd have to invert this half reaction, because one of them would be reduced, but the other one would have to be oxidized, because you have to pair a reduction reaction with an oxidation reaction. And in that case, that would mean that technically the sign of the E0 is also flipped. So there are two ways that you can think about this. You can either just think of when you flip a half reaction, then the sign of its E0 is flipped. Like for example, with this zinc one over here, if it's going in this direction, zinc, and it's gaining 2 electrons, and then it goes into aqueous ion to a solid form, and we're told that negative 0.76 is the reduction potential. If I were to flip this, if zinc were to be oxidized, then in that case what would happen is it would be positive 0.76. Or another way you can think about it is that for a cell, the E naught of the cell should be reduced versus oxidation. Yep. That would be, 1 second, E naught of whatever is being reduced minus E naught of whatever is being oxidized. And then in that case, you can just use the value that you see, even if it's negative, because if you have a negative and a negative, it'll turn out to be positive anyway. So when we go through the actual questions, I guess I can run through both methods just so that everyone is clear on that. Otherwise, like if you're already clear, of course, go ahead and skip to the future question. So that's that. Now let's look at the questions. This first question. If student 3's measurement in table 1 was obtained from a cell made by connecting the unknown solution to a standard zinc electrode in table 2 by means of a salt bridge, which of the following ions was student 3's unknown? So just to clarify what happened in the passage, each student got an unknown, okay, and they have to react it with something that they already know the values of or the properties of to figure out what their unknown would be. So student 3 got an unknown, they reacted it with zinc, right? They reacted it with a standard zinc electrode, and what happened, the nature of their unknown tells us that they got this 1 molar cation, and what they measured was this E naught. So the nature of the unknown doesn't really give us much information in this context, so E naught is probably what's going to help us identify what the actual unknown was. Okay, so we're asked which of the following ions was student 3's unknown. We're given some ions in the answer options. So 1.1 volts. So if E naught of the cell is equal to 1.1 volts, so this is just reduced minus oxidized, and this is 1.1 volts. Well, we don't know whether the zinc was reduced or oxidized, but when I come here and I look at zinc over here in the table and I look at its value, negative 0.76. So for the two to add up and the total to be 1.1, it would have to be something that's very positive. But if I were to add the most positive, like this one and that one together, that doesn't work out. The only way that you can add two things and they add up to 1.1 is this, which hopefully isn't too hard to see. 0.76, if I just think what's going to add up, like if I look at the 70, what's going to make that 100? The 30 will, and then the 4 and 6 also come together to make that extra 1 or 11. So these two should kind of stand out, and the only way to really do this is just by looking at random pairs, pairing the zinc up with different things and seeing which one would give you 1.1, either if you added it or you subtracted it. In this case, these two numbers would come together if I added them. So if it was 0.34 and then I added not negative 0.76, but if I added positive 0.76, then that would give me the positive value. So the only way that can happen is if instead of negative 0.76, it's positive, meaning zinc is oxidized. And in this case, if I did have copper and zinc together, this is the way the reaction would go. Copper has a higher reduction potential, so it would remain positive, the E naught, and then for zinc it would go the other way. So if I was to show that, this is what it would look like. So I have my oxidation reaction, which is my zinc solid. It goes to zinc 2 plus, which is an aqueous solution compound, and then 2 electrons. So this is colon. And then my reduction reaction. So notice what I did. I flipped the half reaction that was inside the table because zinc has to be oxidized. And then the reduction reaction would be copper. And I don't have to balance anything because I see 2 electrons on both sides, so that is good. So copper solid. And then the final reaction from that would be this, aqueous plus the zinc solid gives me, well, terrible arrow, gives me copper solid and then the zinc ion. Okay, and I don't have space really here to show you the addition but of the E naughts, but E naught of this guy, you can think of it as being the opposite, so 0.76 volts. E naught of this reduction reaction stays the same, 0.34 volts, and then I add them together just like I added the half reactions. So therefore E naught for this cell is going to be positive 1.1 volts. Okay, that's one way of thinking about it. Another way is just this over here. So the reduction one, that is 0.34 volts minus negative 0.76 volts. Either way, the negative and the negative will cancel out. Either way, you'll get 1.1 volts. So those are two ways of answering that type of question. That's question one. I'm probably going to erase that afterwards because there isn't a lot of space here, so you guys can come back and see that calculation if you still have trouble with it. And at the end of all that, I say copper is the correct answer. Moving on to question 2. Now student 4 prepared a solution. They dissolved this many grams of the assigned unknown in water to a total volume of this much, and were asked for the molarity. So molarity is just moles over liters. Moles over liters. But first we have to find the moles. We have the liters, which is the volume, 250. But moles is mass over molar mass. Now I have my mass. It's 29.25 grams. And this is student 4 that I'm looking at. So student 4, we're told right here that this person has a white solid and somehow they know that the molar mass of it is 58.5 grams per mole. So 58.50 grams per mole is going to give me my moles, and this is just half, right? If you do 29 times 2 is 58. If you do the 0.25 times 2 is 50. So that's a pretty simple calculation that they gave us. Always love when they do that. So it's half moles. So 0.5 moles. I'm just going to keep it like this because for me, the way that calculations work easier is if I keep it in the fraction form. Some people might prefer to keep it in the decimal form, and you can manipulate math better that way. But for me, if I'm doing like pen and paper style without a calculator, fractions in this case would work easier, because if I plug in my moles, it's half moles, right? And then 250 milliliters is my volume. That is 0.25, right? 0.25 liters, and 0.25 is just a quarter. It's 1 over 4. So 1 over 4 liters. And when I'm dividing something by a fraction, I can just flip the fraction and multiply that. So this thing can just be 1 over 2 times 4 over 1, which means it's 4 over 2, which means it's just 2. So 2 moles per liter. That is my correct answer. So this question, D, is the correct answer. 2 moles per liter, or 2 of that big M. That's my molarity. Okay, moving on to this third question. The name of student 5 is unknown. So we're asked for the name, and then student 5 is unknown. Okay. Here it is. Fe2SO4 3. Fe2SO4 3. Now for this, two parts. First of all, you need to know the naming conventions like sulfate, sulfite for those ions. How do you name them? This is something that you should have already learned, so you can quickly look at SO4 and then say, okay, that's sulfate. It's not sulfite. You should have been able to already do that from the beginning. And then afterwards, you have to figure out what is the charge on the iron. So if you've seen this compound many times, then you've probably seen like H2SO4. And me, I've done so much chemistry that I just know that SO4 has a 2- charge. So when you do that, you know that this will split up into, like if I was to split this up, it splits up into 2 Fe, and then it's going to be 3 SO4, and I know that this one has a 2- charge. So if it has a 2- charge, then charges have to be balanced on either side. So there's a net like 0 charge on the left side. So if I multiply the 3 and the 2 over here, then this gives me -6. So the iron has to be +6 over here, right? So that means that this guy must be +3. So therefore I know that it's iron 3 and not iron 2. So if you're satisfied with that explanation, then you can move on to the next question. But just to go into it a bit further, for some people that are a bit more confused on this, if you were not sure of whether it was like a +2 or not, if this one was +2 or 2+, if this one was like this instead of 3+, then that means that I have a +4 over here, so I must have a -4 over here, and then somehow I have to turn the 3 into a 4, like whatever that is. That would be like 4 divided by 3, so that would be like a 1.33. That makes no sense. So if you were to, if you had no idea and you were just to try it out, like what if there's a +2 charge, then you would see that it doesn't really make sense. And so you should be able to choose the other charge for the iron and figure out that it's 3+ and this is 2-. If you were to draw like a Lewis structure for sulfur, you should know from doing a lot of different questions, especially for like organic chemistry, that sulfur can have 6 bonds. So here we know that it's bonded to 4 oxygens. Sulfur can have 6 bonds. Here's 4 already. Let me start adding my double bonds. So when I do that, only 2 of the oxygens can have double bonds. The other ones have single bonds. And if an oxygen has a single bond like that, it has too many electrons. It has a negative charge, therefore. So that is how the structure will look like because of those 2 negative charges. Like if I ever forget for a sulfur compound or any other compound what the charge is, then I try to draw it out, and I just know from doing a lot of practice that sulfur has 6 bonds to it, so it leaves 2 oxygens with a negative charge, so it's going to be 2-. So those are the multiple ways that you can think about this. And then just to throw in this figure right here, these are some naming conventions. So sulfur, this one over here, right, that's sulfate. If it had 1 less oxygen, then it would be sulfite. Let's look at chlorine over here. This one is chlorate when it has 3. If it has 1 more than that, then it's perchlorate. If it has 1 less oxygen, chlorite. If you go down, hypochlorite. So know all of these different naming conventions and know their charges as well, because that will likely come up in the chemistry section. Very easy thing to come up. So because of all of those reasons, those are different ways that you could have figured out that the sulfur part is not sulfite but sulfate, and the iron part is not 2+ but 3+. Moving on to the next question, and this will be the final question of this passage. Which expression gives the reaction quotient for a spontaneous reaction between standard silver and aluminum electrodes? So we're reacting aluminum and silver. It's a spontaneous reaction, and we want the reaction quotient. Okay, that's what we're looking for. Those are our answer options over there, and I am now going to erase this stuff so that I can do this calculation. So silver and aluminum. That means that I'm looking at this guy up here, this guy down here. Those are the numbers, the E naughts. So in this case, remember that they said it's a spontaneous reaction. That means that my delta G is less than 0, it's negative. And this is an equation for delta G, NF, and then E naught. So N is just number of moles, F is a positive constant, so E has to be positive. E must be positive for delta G to be negative. So a spontaneous reaction automatically means that E naught is positive. So for E naught to be positive, that means that the one that has a higher E naught is the one that's going to be reduced. So silver is the one that's going to be reduced. Aluminum has a lower reduction potential. It's going to be oxidized. So that means that its charge, or its E naught, is going to be negative. Instead of negative 1.66, it's going to be positive. Okay, so positive overall E naught of the cell. So here is my reduction reaction. Silver. Actually, let me draw it a bit over here. Silver, and I have an electron, and it goes to this thing, and then my oxidation reaction is the aluminum, and it is now losing electrons, Al 3 plus aqueous plus 3 electrons. So I just flipped that half reaction. Okay. My E naught, well, firstly I want to say that I have to balance the electrons. Notice how there's 1 electron over here and then 3 for the one on the lower side. If I were to add these half reactions, I would have it being imbalanced, so I can't add them the way that it currently is. I have to do something to make the electrons the same. So the easiest way to do that is just to take the top reaction and multiply everything by 3. If you multiply everything by 3, it's still the same ratio, so it's fine. I can do that. And then now my electrons are going to cancel out, and I can add everything. So let me also add in my E naughts. E naught for the reduction reaction was positive 0.8 volts. And then E naught for this one, sign is flipped, so now it's positive 1.66 volts. Let's write the final reaction. 3 of this silver plus the solid aluminum. That goes towards these products. And then my E naught total is positive 2.46 volts. Okay. I don't think we even needed the E naught, but there it is, just in case. Like, at least you can see that it's positive, so that's why you know that, okay, I did everything right because it's a spontaneous reaction. But what we really needed is this full reaction so that we can see that at equilibrium, what is the constant? We're asked for the reaction quotient, right? Which is Q, but Q, you find it the same way as K. That's what they told us in the passage. And just like with K, if something is solid or a liquid, the concentration doesn't really change much at equilibrium. So we remove those from our final quotient. So therefore our Q, just like with K, is products over reactants. Our product, you can see, is that aluminum ion, so Al3 plus, and our reactant is the silver, Ag plus, and I notice that it has a 3 over here. That's supposed to be a 3, so I put a 3 over here as the exponent. So that's my answer, and that matches up with B and not the other ones. So that's my full answer for 44, and that is the final question in this passage. If you have any questions, make sure to drop them in the comments down below, and we'll keep an eye out on that. Otherwise, thank you for watching. I'll see you guys in the next video.